The subject of these two parts deals with the properties of liquefied gases. In Part 1, the programme was confined to discussion of their physical properties. This programme discusses their chemical properties and later provides a summary of the characteristics of the more important cargoes. Knowledge of the behaviour and basic chemical properties of liquefied gases is of extreme importance when considering the condition of the cargo being carried. Like any other cargo, liquefied gas can become contaminated or damaged if adequate care is not taken. You already know about cargo loss due to vaporization. What we must now ensure is that we know how to maintain the appropriate conditions for the cargo. The majority of gas cargoes carried at sea are derived from the same basic products, which are usually either petroleum or natural gas. In chemical terms, they are known collectively as hydrocarbons. This is because they consist solely of hydrogen and carbon atoms, and the ways in which these atoms combine or bond together vary considerably. Thus, each combination forms a different compound or product. Strange as the names of these gases may sound, they're all just compounds of carbon and hydrogen. This table illustrates the point. Don't let the numbers confuse you. And take, for example, propane. All that we're saying is that each molecule of this gas is made up of 3 carbon atoms and 8 hydrogen atoms. By the way, before we go any further, it's important to remember that the cargoes chlorine, ammonia and vinyl chloride are not called hydrocarbons. The reason is because they do not consist solely of hydrogen and carbon. The properties of some of these typical non-hydrocarbon cargoes will be gone into later. Now back to the subject of hydrocarbons. We start by looking at the carbon atom. The characteristic of the carbon atom is that it has a strong urge to bond itself to 4 other atoms. Here, each carbon bond has been linked with a hydrogen atom to form a tight molecular structure. Molecules such as these are called stable or saturated. Once in this saturated state, the molecules collect together to form a partnership. This means that the molecules don't react with each other unless stimulated by an external source. Unsaturated molecules are another matter. They have few scruples and will seek to accommodate or react with suitable atoms from other sources until their full needs are met. In practical terms, when a gas formed of unsaturated molecules is brought into contact with other suitable gases or substances, they will readily react to form a new product. We've concentrated on the hydrocarbon molecule, but the atoms combining to form any molecule will have their own bonding requirement. In all cases, the stability of a substance or its readiness to combine with other substances will depend upon the level of saturation of its molecular structure. Let's take a look at the structure of some other gases. The chemical formula for this gas, ethylene, tells us that its molecules are made up of 2 carbon and 4 hydrogen atoms. You'll notice that each carbon atom has 4 unaccommodated bonds, while the hydrogen atoms each have a single unaccommodated bond. Now, if we bond them together, we find that we have 2 spare carbon bonds. To fulfill the bonding requirement, the bond between the carbon atoms is in fact doubled up. Both carbon atoms effectively have only been bonded to 3 other atoms. This means that their 4th bond has not been satisfied, and therefore the ethylene molecule is unsaturated. To recap, we talked briefly about unsaturated substances changing their composition to form new substances. The speed at which this change may occur can vary considerably. The change may be very slow and sometimes reversible, or rapid even to the extent of causing an explosion. Again, the degree of seriousness will depend upon the bonding requirements of the molecular structure. Take, for example, acetylene. Although not a normal cargo, this serves to illustrate the point. You'll notice that the formula tells you that the molecule contains 2 atoms of carbon and 2 atoms of hydrogen. We now have a molecular structure with 3 bonds unaccommodated. To meet the bonding requirements, there must now be a triple bond between the 2 carbon atoms. The molecular structure is more correctly illustrated here, showing the triple bond. Let's now compare this with the other 2 gases we've discussed. If we consider these 3 gases, it can be seen that the least saturated of the 3, acetylene, is also the most unstable. In fact, if we consider their application ashore, natural gas is used for domestic heating and cooking, whereas acetylene is used in gas welding. One rough method of assessing the stability of a hydrocarbon gas is to study the ratio of carbon and hydrogen atoms in a molecule. Any gas nearing a 1-to-1 ratio is particularly unstable. One method by which a cargo can change its state is by polymerization. This is the combining of individual molecules to form large or even giant ones. These large, newly formed molecules are known as polymers, and their characteristics will differ greatly from the original compound or product. Whether polymerization is likely to occur or not will depend upon several factors. For instance, the molecular structure of the cargo, the pressure and temperature at which it's carried, and the inclusion of any impurities. Contamination of the cargo by impurities, whether loaded with the cargo or introduced on board, may encourage the polymerization process. The amount of contaminant necessary to start the process may be small. A lubricating oil leak in the reliquefaction plant, or a residue in a loading pipe from a previous cargo. Whatever the cause, the value of the cargo to the shipper will have been seriously affected. Some cargoes, such as butadiene, may combine with a plentiful supply of air or oxygen to form explosive peroxides. Peroxide formation is reduced or prevented by the use of compounds known as inhibitors. These inhibitors can be of two types: those which break down existing peroxides and those which prevent the formation of further peroxides. Whatever inhibitor is used, its effectiveness will depend upon its introduction in sufficiently large quantities. It's also important that the inhibitor stays in the liquid phase and is not handled by the compressor. It's also vital that the reliquefaction plant contains no inhibitor, or else serious damage may result. Remember, inhibitors may be poisonous. This brings us on to another matter: leak detection. Both liquid petroleum and liquid natural gases can be dangerous. Therefore, it's important that leaks are detected quickly. One method of achieving this is to give the gas a specific smell, and this is accomplished by adding an odorant. Odorants are organic compounds containing sulfur, the most common being formed from chemicals known as mercaptans. Particular care is taken to ensure that the proportion of odorant to cargo is sufficient to provide a strong enough smell without being poisonous to personnel or harmful to the ship's plant. We'll now briefly summarize the chemical and physical properties of these more common cargoes. It should be remembered that there will be slight variations in the purity of each gas. The differences in characteristics may be critical, so always check this point and use the most accurate and reliable information source available. Propane, also known as dimethylmethane, is a member of the alkane or paraffin series of saturated hydrocarbons. The chemical formula is C3H8, and if we examine the molecular structure, we verify that it's a saturated compound. The molecular construction is divided into one general formula for saturated molecules and three separate formulas for unsaturated molecules. Propane falls into the alkane group. Its boiling point is -43 degrees centigrade at 1 bar, and it's a colourless, flammable gas.